Okay, we're ready to pick up now. We've just done a uh, problem involving an inelastic collision where the two objects hit and stick and kinetic energy is not conserved because there's damage done, and that damage does work and it removes some of the kinetic energy from the system. So now there's also cases where there's no damage done during collisions. Take, for example, billiard balls that hit each other on the billiard table. They suffer no permanent deformation because of that collision. And in that case, you can model that as a system that doesn't have kinetic energy lost. If there's no kinetic energy loss, then it's an elastic collision. Elasticity is the ability of an object to be deformed and then, upon the release of the force that deformed it, go back to its original shape. So, with that kind of a collision, there's no work done by the two objects, no net work done by the two objects on each other, and so there's no loss in kinetic energy. Momentum is still conserved, though. So, here we go. Elastic collisions, kinetic energy doesn't change for the system, no permanent damage done to the objects, what I just said. Okay, now you can state that mathematically like this. Momentum is still conserved, P initial is equal to P final. Kinetic energy is also conserved, K initial is equal to K final. So here we've got two criteria that need to be met for a elastic collision, where we only had one criteria that had to be met for inelastic collisions. Only momentum was conserved in the inelastic collisions. In elastic collisions, like what we're going to talk about now, both quantities are conserved. So here goes. You've got two blocks that are sliding to the right along a frictionless surface. The block on the left is a 1 kilogram block moving at 2 meters per second. The block on the right, 4 kilogram block moving at 1 meter per second. So they're going to hit, click, and they're going to have some final speeds after the collision. But now they're not connected together, okay? They just hit and then part. And what we want to do is find out what the two final speeds are after this collision, VA and VB. VA being the final speed of the 1 kilogram block, VB being the final speed of the 4 kilogram block. Okay, now what we need to do is find the initial momentum, set it equal to the final, find the initial kinetic energy, set it equal to the final. So I'm doing that up here. The initial momentum of the two block system is going to be the mass of the first block times its velocity, so 1 times 2, there's the 2, plus the momentum of the other block before collision, and that's going to be the mass of that block times its velocity, so 4 times 1 is 4. 2 plus 4, 6 units of momentum. I'm not writing the actual units in there just because it gets so busy, but we know the units are momentum units, kilograms, meters per second. So you've got 6 units of momentum before the collision, so you better have 6 units of momentum after. Now, the final momentum will be equal to the mass of the first block times its final speed, VA, which we don't know, so we have to express symbolically. So 1 times VA is just VA, okay, plus the momentum of the other block, which is going to be 4 kilograms times VB. So that's 4 times VB. I'm not writing the units either. So now this should be equal to this, right? So 6, the original momentum of the two block system is equal to this, the final momentum of the two block system, in terms of two unknowns, VA and VB. So we've got one equation with two unknowns. We can't solve for those two unknowns. We need another equation with the same unknowns in order to solve for both. So we get that from doing the same thing we just did with momentum for kinetic energy. So the initial kinetic energy of the system before collision is going to be 1/2 times the mass of the first thing times its velocity squared. Okay, so 1/2 times 1 kilogram times 2 meters per second squared, then plus the kinetic energy of the other thing before collision, so it's going to be 1/2 times 4 kilograms times 1 meter per second squared. And if you do this, you get 4 joules. Okay, so the total kinetic energy of both objects together before the collision is going to be 4 joules. Now, the kinetic energy for the final case is going to be 1/2 times 1 kilogram times VA squared plus 1/2 times 4 kilograms times VB squared. Now, I didn't like the fact that I had a 1/2 in this factor, so I'm multiplying this equation by 2, so I have to multiply this equation by 2 because, you know, they're just two different sides of the same equation, right? So if I do that, I get 8 here, and then this becomes VA squared plus 4VB squared. So I got this equation from setting the initial kinetic energy equal to the final kinetic energy. I got this equation from setting the initial momentum equal to the final momentum. And those two equations have the same two unknowns, so we should be able to solve for those unknowns. So the way I'm going to do it is like this. I'm going to isolate VA here. So I'm going to subtract 4VB from both sides. So I get VA by itself is equal to 4VB minus 6. Now, I'm going to take this way of representing VA and plug it into the second equation, substitute it in using substitution, right? Okay, so I have to square it though, right? I've got VA here, but I want VA squared there, so I'm going to square this. So the left-hand side squared is just VA squared, that's what I want. Now I have to square this side. It's two terms, so you FOIL it if you're going to square it, and you get 16VB squared minus 48VB plus 36 if you square this binomial, okay? Now I can take this way of writing VA squared and plug it in here, which is what I'm doing down here. So I've got the 8 here is equal to VA squared, which is going to be all of this, plus 4VB squared. Now I've already got 16VB squared in the VA squared expression, so if I add 4VB squared to it, I get 16 plus 4, I get 20VB squared, then the minus 48VB, then plus 36, okay? So now I'm going to subtract 8 from both sides of this, so 36 minus 8 is going to be 28. So I get this expression right here. So now this is in standard form, it's second order, it's a quadratic, right? So I can simplify that because every one of these coefficients is divisible by 4, so I divide both sides of the equation by 4, and I've simplified it down to 4VB squared minus 12VB plus 7 is equal to 0. This one was easy enough with the coefficients that I could solve it by inspection, and I ended up with these two binomials multiplied together. So, 5VB minus 7 times VB minus 1 is equal to 0. Now that's going to be true only if this factor is 0, or if this factor is 0, or if they're both 0, right? So if we set this one equal to 0 and then solve for VB, we get VB is equal to 7/5 meters per second. And if we set this factor equal to 0 and solve for VB, we just get 1 meter per second. Okay? Now, one way to lend some validity to your answer is to see if one of these answers is the original speed of block B. And it turns out, yes, the original speed of block B is 1 meter per second. So that's one of the answers. That's almost a guarantee that this other answer is definitely the correct answer, that will conserve both momentum and kinetic energy in the two-block system. So what this tells you is that these two answers is, hey, if these two blocks miss each other during the collision, guess what? Momentum and kinetic energy are conserved if there's no actual collision. Okay, but that's kind of stupid, right? But it is mathematically true. It's not wrong. So the other answer is going to be conserving kinetic energy and momentum if there is a collision. That's the one we want. So during the collision, what happens is the second block, the 4 kilogram block, is sped up from 1 meter per second to 7/5 meters per second. So it's sped up by 2/5 of a meter per second, right, due to the collision. That probably means that block A is slowed down, right? So now we want to find the velocity of block A. Well, now that we've got the velocity of block B, we can plug it in right here and solve for the velocity of block A, which is what I've done up here. And I get that the velocity of block A is negative 2/5 meters per second. So block B is sped up to 7/5 meters per second, and block A is slowed down to the point where it's actually moving backwards now. The negative sign means that it hit, bounced, and now it's going backwards at a slower speed of -2 meters per second. So there we have solved a problem involving elastic collisions where there's conservation of kinetic energy and momentum. Now, the next topic in line is going to be doing momentum problems involving 2 dimensions. So in that case, remember, a 2-dimensional problem is really just 2 one-dimensional problems. We've learned how to solve one-dimensional problems for elastic collisions and inelastic collisions now. And now we can solve, now we're going to use this technique in a 2D problem. But here we go, 2D momentum problems. The x component momentum before the collision is equal to the x component momentum after, and the y component momentum before the collision is equal to the y component momentum after the collision. We're going to use that in the next problem. Now, the 2-dimensional problem that I have in mind is over here. All right, I've got 2 blocks that are coming at each other perpendicular. Block A is moving from left to right horizontally. It's got a mass of 2 kilograms, and it's moving at a speed of 4 meters per second in the x direction initially, going this way. Block B is 1 kilogram, half as massive as block A, and it's moving upward vertically at a speed of 6 meters per second in the y direction initially. And then they come up here, crash, they hit each other, and they stick together, and then they slide off into the first quadrant here. Okay, we don't know what the final speed is, we don't know what the final angle is, we don't know the direction or the speed, we don't know the final velocity. And we're going to use conservation of momentum in both the x and the y direction to solve this. Okay, so remembering that one single 2-dimensional problem is 2 one-dimensional problems. Come on over here. We're using the initial is equal to the final momentum, conservation of momentum. In the x direction, the initial momentum is the momentum of the block that's sliding in the x direction, 2 kilograms, its mass times its velocity, 4 meters per second. You get 8 kilograms meters per second in the x direction. The final momentum of the single object, which is now the 2 blocks melded together, is going to be its total mass, the mass of both blocks together. So it's going to be 3 kilograms times whatever its velocity is times the cosine of the angle that it's moving at. That'll be the component of the velocity in the x direction, right, using cosine. Now we can simplify that down to this, and then we set this equal to this, the initial momentum in the x direction equal to the final momentum in the x direction, and we can simplify that down to 8 is equal to 3 v final cosine theta final. So basically in this one equation we have 2 unknowns, v final and theta final, the 2 things we want to find, though we can't solve yet. We need another equation. We get that by doing the same thing that we just did in the x direction, but now doing it in the y direction. So now in the y direction, the initial momentum is going to be the momentum of the block moving in the y direction. Its mass, 1 kilogram times its velocity of 6 meters per second. That works out to 6 kilograms meters per second in the y. And the final y component velocity of the 2 blocks melded together will be its total mass, 3 kilograms, times the component of the final velocity in the y direction, which is v final sine theta final in the y. And now if we set the final momentum of the y equal the initial momentum of the y, we get this, 6 is equal to 3 v final sine theta. So now I brought both of those equations over here. I've divided through by 3 on both sides. And I've got basically 2 is equal to v final sine theta. And 8/3 is equal to v final cosine theta. Now I'm going to divide this equation by this. Remember, this is a true statement and this is a true statement. I can divide this one by this one and get a third true statement, and that works out to 3/4 is equal to sine theta. The v finals cancel. That's nice. One of the unknowns is gone. Okay, if we isolate v final, it's the inverse tangent of 3/4, which is about 37 degrees, 36.9 degrees, something like that. Now, if we go ahead and take that value for the angle and plug it back into either one of these, I plugged it into this one, and isolate v final, then that works out to 2 divided by sine 37, which is 3.33 meters per second. Okay, so we found the direction and the velocity, or the direction and the speed for the two blocks after the collision. It slides off 37 degrees clockwise from the x-axis at a speed of 3 1/3 meters per second after the collision. There we've used conservation of momentum twice in the same problem to solve a two-dimensional conservation of momentum problem. Okay, now the last section in this chapter has to do with conservation of angular momentum. So first we have to introduce the idea of angular momentum, and I'm going to go back to some of the linear rotational analogs that we've dealt with before when we were talking about rotational motion before. So linear, you can express acceleration as force over mass, right, using Newton's second law. The rotational analog to that would be alpha. Remember, that's angular acceleration, and that's going to be equal to torque divided by rotational inertia. Remember, torque is the rotational analog to force. Rotational inertia is or angular, or rotational inertia is the rotational analog to mass. Now, also, you can solve for A in terms of the first equation of constant accelerated motion. It'll be v final minus v initial divided by the time between these two velocities, delta t. We've got a similar equation in the four equations of constant angular acceleration. So the angular acceleration will be equal to the final rotational velocity minus the initial rotational velocity divided by the time between those two rotational velocities. Now remember, these two are only true if you've got constant acceleration or constant angular acceleration. But that'll work for this case, where we can take this down to an instantaneous point where the accelerations can be considered constant. So in any case, this equation, F times delta t is equal to m times delta v. Remember, this is the impulse momentum theorem, or the impulse equation is often called. The force on an object times the time that force is applied is equal to the mass times its change in velocity. Now, corresponding to that in the rotational version, you've got torque times the time torque is applied is equal to the rotational inertia of an object times its change in rotational speed. Now you can rewrite this equation, the right-hand side being two terms, because delta omega is omega final minus omega initial. So the torque times the time the torque is applied is equal to I omega final minus I omega initial. And I omega is like momentum, right? Because force times delta t is equal to the final momentum minus the initial momentum. So the rotational analog for momentum is called angular momentum, and it's equal to I omega. Kind of makes sense, right? Because I is the rotational analog to mass, and omega is the rotational analog to velocity. So linear momentum is mass times velocity. Angular momentum is rotational inertia times rotational velocity. Okay, now taking that new definition of angular momentum, if the sum of the torques on an object is 0, if all the torques added together equals 0, then that necessarily means if the torque is 0, okay, then the change in the angular momentum must be 0, right? And if you've got a 0 on this side, you have to have a 0 over here. So if the angular momentum is 0, that means that the final angular momentum minus the initial is equal to 0, or it doesn't change. Initial momentum equals final momentum. And here, this is the conservation of angular momentum. So just like linear momentum is conserved quantity in an isolated system, angular momentum is also a conserved quantity in an isolated system. Okay, now I've put a problem up on the board that involves conservation of angular momentum. Remember, angular momentum is rotational inertia times rotational speed. So here I've got like an old-fashioned record turntable, and it's just revolving on a frictionless surface. It's not being driven by a motor now. It's just rotating at a rotation speed of 10 radians per second. Now its mass is capital M, which I said was 2 kilograms. Its radius is 1 meter. So an extremely large turntable. And onto it is dropped a piece of putty. And it's got a mass little m, and I'm saying that mass is 1 kilogram. So now what it's going to do is it's going to drop down and stick to the rim. So this is the before picture, this is the after picture. Now that's going to slow down the rotation rate by how much? So what we want to do is find the final rotation rate of this once the putty has hit the surface, and now it's rotating at a slower rate. So to do this, what I have to do, since I need the angular, the rotational inertia and the angular speed, I have to find the rotational inertia. Now the rotational inertia of a rotating disk, if you go back to the chapter where we did this, it's 1/2 times the mass of the disk times its radius squared, and that works out to 1 kilogram meter per second squared, and I'm sorry, 1 kilogram meter squared. And the final rotational inertia of the system with the rotating disk and the blob is going to be the original rotational inertia of the disk plus this new term due to the rotational inertia of the blob of putty, and that's just going to be its mass times its distance out from the center of rotation. So now that works out to 2 kilograms meters squared. So notice the initial, the final rotational inertia, final is twice as big as the initial. Now conservation of angular momentum tells you that the initial angular momentum is equal to the final. So that means that rotational inertia initial times rotational speed initial is equal to rotational inertia final times the rotational speed final. We want to find the final rotational speed, omega final, that's going to be I initial omega initial divided by I final. So if you plug in all the values, you find the final rotational speed has been cut down from 10 radians per second down to 5 radians per second. So it's spinning half as quickly as it was before the blob of putty stuck to the surface. Okay, now that concludes all of the major topics in Chapter 9, momentum. And what I would recommend you doing is a lot of problems out of the back of that text. Now, the way I have to quiz you and test you is, of course, online. So we're going to have multiple choice tests, but I can choose semi-demanding problems that, still require you to do the work in order to come up with the answer, or you can guess, I guess. But in any case, that's what we're going to be doing. And in order to get this down, you need to be doing problems out of the back of Chapter 9. Feel free to call me, and remember my number is 407-222-0803. So here it is. Call me, and you can text me the problem that you're having difficulty with, and I'll go through it with you over the phone. So, or if it's good enough problem, I'll do it up on the board like this, and everybody will get to see it. So everybody, take care, stay safe, and I will talk with you again soon. and expect a quiz sometime soon online.